In this video, we will learn how to correctly predict the loose dot structure for molecules that have an expanded octet. So the way we will do it is we will first follow the loose dot structure guidelines as I outlined in my video before for regular loose dot structures, and I have shown them here also, which is calculate total number of valence electrons, connect atoms to one another using bonds, subtract electrons used in bonds from the total valence electrons, use remaining electrons to make outer atoms happy, and so on. We will definitely practice it, so you don't have to worry about reading all the rules. We will go with them one by one. And now we will also talk about expanded octet. So we will have to check if our central atom is in row 3 or below. Let's just look at the periodic table to check that. So on the periodic table, this is row 3. So if we have atoms like phosphorus, sulfur, chlorine, argon, or below, everything below also, then they're capable of having an expanded octet. They might not have it, but they're capable of having it. So if we see that we have those molecules, we have to be aware that an expanded octet can happen. Now, how would we know if there is an expanded octet? And if we need to change our loose dot structure, we will have to calculate formal charges, which I will show you how to do as well. And if we calculate that the central atom has a formal charge, we will have to give it double bonds. So without further ado, let's just write the 3 examples that I have. Let's call these A, B, and C, and we will see how the professor can trick you with giving you molecules that have an expanded octet and how we have to be careful and draw each loose dot structure correctly. So let's start with PF5. Okay, we will go through my guidelines. First, I have to calculate the total number of electrons for PF5. If you look at the periodic table, phosphorus is here, and it will have, these are the group numbers 1, 2, 3, 4, 5, 6, 7, and 8, and these represent how many valence electrons each element has. Phosphorus is in group 5, it has 5 valence electrons, so we will do 5 plus. Now let's take a look at fluorine and see how many valence electrons fluorine has. So fluorine is in group 7, so it has 7 valence electrons. And there are 5 fluorines, so times 5. 7 times 5 is 35 plus 5, we get 40 electrons that we can use. Next, we connect atoms to one another using bonds. So let's go ahead and do that. I'm just going to connect phosphorus to fluorine. There are 5 fluorines, so I will connect my phosphorus to 5 fluorines. Already you notice that phosphorus has more than 8 electrons around itself. If you count, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can phosphorus have 10 electrons? Can it have an expanded octet? Well, we see phosphorus is in row 3 or period 3. So yes, it can. So this is an expanded octet example. We just use 5 times 2, we just use 10 electrons, and we have 30 left. And we will give each fluorine 6 electrons for it to be happy, to have an octet. 1, 2, like this. And each fluorine gets 6 electrons. We just use 6 electrons times 5, which is 30, so we just used all of them, and it's equal to 0. Now what we're going to go ahead, so we have no electrons left, and it seems at first glance that all of the fluorines are happy because all of them have 8 electrons, and the phosphorus has 10 electrons. So next we will calculate formal charge. To calculate formal charge, I'm just going to abbreviate it Fc. It's basically number of valence electrons minus number of bonds plus lone electrons. I abbreviated a lot so it fits in. So let's do it for phosphorus. We said phosphorus had 5 valence electrons minus, how many bonds does it have? 1, 2, 3, 4, 5. 5 plus, how many lone electrons does it have? None. We had no electrons left, so we didn't put any. So 5 minus 5 is equal to 0. This phosphorus is happy, so we can leave this molecule alone. So this molecule was a case of an expanded octet where phosphorus has more than 8 electrons, and it's capable of having more than 8 electrons because it's located in row 3 or below. In this case, it's located in row 3 or period 3. And now we're going to go ahead and it had the formal charge of 0. Now we're going to go ahead and do XeO3. Xe, I'm just going to tell you, it's in group 8, so it has 8 valence electrons. And then oxygen has 3 valence electrons. There are 3 oxygens and each one is 6 valence electrons. So 3 times 6 plus 8 is equal to 26 electrons. Now we connect all of our atoms together. Xenon is in the middle and it's connected to 3 oxygens. So I'm just going to connect it to 3 oxygens. I use 3 bonds. Each bond has 2 electrons. So I'm going to 3 times 2 is 6. So I used 6 electrons and I have 20 left to work with. I always take care of outer atoms before I go to the central atom, like my chart said. Again, you can watch my loose dot structure video for regular molecules prior to this to familiarize yourself with it. But this oxygen right now has 2 electrons because of the bond, so I have to give it 6 more so that it has 8. Every atom wants to have 8 except for hydrogen. And like you see here, some atoms might have more than 8 if they're essential atoms in period 3 or below. I just keep on repeating it so you will remember. So I'm going to give each oxygen 6 electrons. Oops, I did not mean to do that. Let me get rid of that. Okay, now we have used, how many electrons have we used? 6 times 3 is 18. We used 18 electrons, which means we have 2 left. So the 2 electrons will go on xenon. And now we have none left. Next, what we're going to do is we will figure out the formal charge of the formal charges of the atom, specifically of the central atom, but we will do the oxygens as well. So we said xenon had 8 electrons. Its number of valence electrons, it has 8 valence electrons minus number of bonds. There are 3 bonds plus 2 electrons. My pen is not really cooperating with me, so let me rewrite like this, and this is plus 3. So right now, even though everyone has looks happy, by the way, when you check xenon on the periodic table, just go ahead and check to make sure. You see xenon is in period 3 or lower. It's lower, it's below period 3, so it can have an expanded octet. So when we checked that xenon can have an expanded octet, and we just said that it has a formal charge of plus 3, that means we will have to give it extra double bonds to get rid of its formal charge. If you do the formal charge on the oxygens here, you will see that each one of these oxygens has a -1. So this is not the best loose dot structure at all because it has so many charges. Now, how many double bonds we will give xenon? It has plus 3, which means it's lacking electrons, so it will want 3 double bonds. So let's go ahead and we will use our lone pairs in the oxygen. So each oxygen will donate one of its lone pair to make itself and xenon happier, and to give a double bond to xenon. Okay, now let's count again. Xenon is 8 minus, how many double bonds does it have? 1, 2, 3, 4, 5, 6. Oops, I forgot a lone pair here. Otherwise, it would not have been working out. So it has 6 double bonds plus, how many electrons does it have? 2. So look at this. 8 minus 8 is 0. Now, in this loose dot structure, xenon is happy. It has no formal charge. If you do the formal charge for oxygens, you will see that they will be 0 as well. So just to reiterate, when we saw this molecule, we first used our regular loose dot structure guidelines to figure out the loose dot structure of this molecule. Then we noticed that xenon was below period 3, so it was capable of having an expanded octet. And then we calculated the formal charge to find out that xenon has a +3 charge, while oxygens are -1. Since it can have an expanded octet, we went ahead and we gave it extra double bonds. We used the lone pairs from the oxygen to give the double bonds. And because its formal charge was +3, we gave it 3 extra double bonds. And so when we calculated our formal charge again, we found out that now xenon has 0 formal charge and oxygens are 0 as well. So this is the correct loose dot structure for this molecule, which is definitely a much more complicated case of the loose dot structure. And let's go ahead, this was our B. Let's go ahead and do our example C, H2SO4. H has 1 valence electron because it's in group 1 times 2, plus sulfur has 6, plus there are 4 oxygens, and there's 6 also. So let's do 4 times 6 plus 6 plus 2, and we will get 32 electrons, valence electrons to work with. For sulfur, the way it looks is it's connected to 4 oxygens like this, and 2 of the oxygens have a hydrogen as well. Now, let's go ahead and take away the electrons we already used in bonds. We have 1, 2, 3, 4, 5, 6 bonds. Each one has 2 electrons, so that's 12 electrons that we have used, which means we have 20 electrons left. And as always, we take care of the outer elements before we go to the central one. So this oxygen needs 6 more, and this oxygen needs 6 more. So I already used 12, and I have 8 left. And this oxygen needs 4 electrons more to be an octet, to have 8. 1, 2, 3, 4, 5, 6, 7, 8. Now it's happy. And 4 more again, and I have used all of my electrons. I have nothing left. Now, even though everything looks great here, everyone has an octet, you can say that's it, the molecule is done. We say hold on a second. We look at the central molecule, at the central atom, which is sulfur, and again we go to our periodic table and we notice that sulfur is in period 3, which means it can have an expanded octet. Therefore, we need to go ahead and calculate its formal charge. Sulfur has 6 valence electrons because it's in group number 6, and we have to subtract number of bonds plus lone electrons on sulfur. Sulfur has 4 bonds, 1, 2, 3, 4, and it has no lone electrons. Therefore, there is a formal charge of sulfur which is +2. If you check the oxygens, you will see that the formal charge on each oxygen will be -1. And so because sulfur is capable of having an expanded octet, and when we calculate it, it has a formal charge. This molecule has a lot of formal charge. we will want to change our loose dot structure so that sulfur will have no formal charge. Since its formal charge is +2, that means it wants two new double bonds to make it happy. So, and since these are the oxygens that have a -1 charge, that means they want to get rid of the electrons. They have too many. So what we're going to do is we're going to make two double bonds with the two oxygens that had too many electrons, and we will leave these oxygens as they were since they had no formal charge. And so our molecule now looks like this. So let's go ahead and check and calculate the formal charge of sulfur now. The formal sulfur has 6 valence electrons, minus has 1, 2, 3, 4, 5, 6 bonds, and no lone electrons. So therefore its formal charge is 0. Now if you check the formal charges of all of the atoms in this molecule, everything will have 0, which means this is indeed the correct loose dot structure. And the way you would know it is first you would, again, just to reiterate, first you would figure out that sulfur is in period 3 or lower, in this case period 3, so it can have an expanded octet. And when we calculated the formal charge, it had a formal charge, so we gave it extra double bonds to make everyone happy, and now my molecule has no formal charges, so that must be the correct molecule for C. This is Maya from Transformation Tutoring. I hope you enjoy my video. Please comment, ask me questions, and I look forward to seeing you in more of my organic chemistry and general chemistry videos.